Welcome to the next video. In this video, we'll be looking at properties of roots, specifically multiplying roots, nth roots. So in this case, when we remember back to what we did previously, when we worked with square roots, we had this rule. If we had the square root of a times the square root of b, we could combine those to become the square root of ab. So we could work forwards this direction, or if we had the square root of ab, we could work backwards to split it up into different perfect squares of which we could take the square roots. So using this formula, or that property, we can extend that to nth roots. Now these are all just examples of our exponential properties. This is really a to the 1 over n times b to the 1 over n. And if we look at this rule here, a to the m times b to the m, if we change those to fractions, we can combine them with one exponent. So we're really looking at an exponential property here. So when we are looking at multiplying roots like we have here, I'm going to write this down because this is a really key important piece, but I'm actually going to write it the other direction. So I'm going to write the nth root of a times b is equal to the nth root of a times the nth root of b. Let's look at a couple examples that use this. So in our first example, I want to look at the square root of 32x to the 8th. This is a square root rule. We've already used this and we've already done similar things, but just as a refresher on how we work with this, I can keep this all in square roots and turn this into the square root. If I want to write 32 as a perfect square times something else, 32 is 16 times 2, and I know 16 is a perfect square, times x to the 8th. And I know x to the 8th is also a perfect square. So then I could rewrite this as the square root of 16 times the square root of 2 times the square root of x to the 8th. This is the square root of 4 squared times the square root of 2 times the square root of x to the 8th using this property could be rewritten as x to the 4th squared. So I'm writing things that can be perfect squares as perfect squares. So the square root of 4 squared is 4, the square root of 2 stays inside, and the square root of x to the 4th squared, square root and squared cancel, gives me x to the 4th. Looks a little better if I write 4x to the 4th times the square root of 2. If I had taken at any of these steps and turned this into a rational exponent, I'm going to jump to this step. This would be 4 squared raised to the 1/2 times 2 raised to the 1/2. And actually, I'm going to go to this one and write this as x to the 8th raised to the 1/2. And the reason I'm going to do that is this becomes 4 to the 2 times 1/2 using this rule becomes 4 to the 1, 2 to the 1/2. I can't do anything with those exponents, but these exponents 8 and 1/2 multiply. 8 times 1/2 is x to the 4. So if I rewrite it in the form I was given, I have 4x to the 4th times the square root of 2. Same answer, two different methods. So the other example I want to look at is what if I have the 4th root of 16, a to the 24, b to the 13. So here is a 4th root. Similarly, I can either work through it looking at my radicals, or I can switch over to rational exponents. It's going to be my decision and whatever I'm more comfortable with. So I first want to look at, are these things something raised to the 4th power? So I am going to rewrite these in exponential form. So 16 I know is 2 to the 1 is 2, 2 to the 2 is 4, 8, 16. It's going to be 2 to the 4th. A to the 24, well, I could rewrite this similar to how I rewrote 8 here. 24 is divisible by 4, so I could rewrite this as a to the 6 raised to the 24. 13 isn't quite divisible by 4, but if I rewrote it as b to the 12 times b to the 12 is divisible by 4. So I'm going to break this up using this property. So I have the fourth root of 2 to the 4 times, that should just be 4, not 24. The fourth root of a to the 6 raised to the 4 times the fourth root of b to the 12. And b to the 12 I can rewrite as b cubed raised to the 4th times the fourth root of b. Okay, this fourth root of b I can't do anything with, but the fourth root of 2 to the 4 is 2. The fourth root of a to the 6 to the 4th, the 4th and the 4th cancel, so this is a to the 6. 4 and 4 cancel, b cubed, and then the fourth root of b stays inside there. I can also, at this step, switch over to rational exponent. So that would give me 2 to the 4th raised to the 1/4 times a to the 24 raised to the 1/4. I'm actually going to go all the way back up to the start, and I have b to the 13 raised to the 1/4. 4 times 1/4 is 1, so that's just 2. 24 times 1/4 is 6, so that's a to the 6. And this gives me b to the 3.25, or 3 1/4. The 3 is fine, but the 0.25 is not. So this becomes 2 times a to the 6 times b cubed times b to the 1/4. That's the decimal there. 0.25 is 1/4. And I want to write it in my original form. 2a to the 6 b cubed times the fourth root of b. Two methods, same answer. Now, there is a caution. We have to be careful when we're working with this. And the reason that we have to be careful is, what if the index is different? This property here, this property has the same index for both of these. You may only combine two radicals into one if the index is the same. If the index is different, you must move your system into rational exponents. So this would become f to the 3/2, because this has an implied index of 2. And this is the cube root of f squared, so that would become f to the 2/3. Based on our properties of exponents, I have the same base raised to exponents. I'm going to add them. So this becomes f to the 3/2 plus 2/3, and I have to do that math. So 3/2 plus 2/3. I need a common denominator. This gives me 9/6 plus 4/6, which is 13/6. So this is f to the 13/6. 13/6 is 2 1/6. You can't have a rational exponent that's bigger than 1, because this is the same thing as the 6th root of f to the 13. And we don't like this number inside to be bigger than the index. So what I need to do is use this fact, the fact that 13 is 2 plus 1/6, to rewrite this as f squared times f to the 1/6, which could be rewritten as f squared times the 6th root of f. This is an equivalent statement to this up here, but this is considered simplified.